Okay, Lesson 13, States of Matter and Phase Changes, Part 2. So I wanted to show you a diagram, a little animation of solid, liquid, and gas. So here we have an example of water, right? And so we have water in the solid form, ice, the liquid form, water, and the gas form, water vapor. And what we have is sort of an enlargement of what the particles look like in each state. So notice how regular the water molecules are packed together in ice, and then how they are randomly moving around each other, not in a regular arrangement. And then they're going to be moving quite a bit faster and have a lot more space in between them if we heat up the water, and it becomes water vapor. So we'll watch a moment of this animation here.
The difference in particle movement across the three states of matter, solid, liquid, and gas, explains the unique properties of each state, including their shape, volume, and how they respond to changes in temperature and pressure.
And gas. So let's try page 2 here. So here's some diagrams of water in its three states of matter, solid, liquid, and gas. Now, here's a question that you'll answer. What do we call the bonds between water molecules? So we see them here in the ice form, and we see them here in the liquid water form. It's not the bonds inside of a water molecule, but the bonds between water molecules. So you'll answer that. Coming back here, if you said hydrogen bonds, you were correct. And in ice, these bonds are very stable. So notice it's like a crystal structure. They're going to stay in the same place, these bonds. And then in liquid water, if we add enough heat, the water molecules vibrate, move with enough energy that those hydrogen bonds break. But what happens is they break and they reform. In liquid water, they're constantly breaking and reforming. And this little diagram here, I think that's what that little yellow thing means, is it's a bond forming or breaking. And that's why liquid water still stays together. If you pour liquid water out into a cup, you have a stream of water that stays connected, but it's not strong, and you can still put your hand through water, right? It's not like ice. We can't put our hands through ice. Those bonds are very rigid and stable. Water, we could break the bonds and slide our hand through, and then they'll reform. And then when we add even more heat, we get water breaks into the vapor form. And here we have individual water molecules moving so fast that hydrogen bonds are not forming between them. So they're just individual water forms, and we can't even see it in the air. Actually, if we see steam, that's still little water droplets. Water vapor is invisible because those water molecules are so small. Okay, so let's talk about a scientific definition for temperature. Temperature is the average kinetic energy of the particles in a sample of matter. So there's our science definition. What does that mean? What is kinetic energy? Kinetic energy is the energy of an object due to its motion. And when an object is moving fast, we say it has higher kinetic energy than when it's moving slow. And the kinetic energy of a particle depends not just on its speed, or it could be the kinetic energy of a larger object than a particle, like a car. The kinetic energy of a particle or object depends both on its speed, which we call velocity, right? Or speed, both the synonymous terms. Velocity also refers to the direction it's going, but velocity or speed of a particle, and on its mass. So there's a formula for that. Ke stands for kinetic energy. So we have kinetic energy, Ke, and we have mass, that's the M, and then we have velocity, that's the V. And when we measure the kinetic energy of an object, the unit we use is called joules. And there's going to be a little question here. You're going to look at this formula and think to yourself, in which state of matter does water have the highest kinetic energy? Solid, liquid, or gas? Okay, coming back, here is a little table that shows us some melting and boiling points of some common substances. Here's our friend water. Water melts at 0 degrees Celsius and boils at 100 degrees Celsius. And you might think, wow, what a coincidence that it's those really nice even numbers, 0 and 100. That is actually designed that way. So that's how they decided what Celsius was. They said, okay, Celsius is going to be the temperature where water, at which 0 degrees Celsius is where water freezes, and 100 degrees Celsius is where it boils. And now we can compare it to some other things like table salt. Table salt, to melt table salt, takes a lot of energy, 800 degrees Celsius. So we can't do that in like a regular oven. To boil salt takes even more energy, 1,465 degrees Celsius. Or gold, right? Gold, to melt gold takes even more heat. And to boil gold, a lot of heat. But then we look at things here. So these are solid at room temperature, right? Not the acetic acid, it's vinegar. And this is liquid. Now these things up here, like hydrogen, boils at it becomes a gas at a really low temperature. It becomes it becomes a liquid at a very low temperature, much lower than we have on Earth here naturally. And then it boils at a really low temperature, meaning it becomes a gas. So these really low melting and boiling points, these substances are gases at room temperature, because room temperature is always higher than these low temperatures, right? So it's going to be a gas at room temperature. Okay. Last thing, plasma, the fourth state of matter. Plasma contains positive ions and free electrons. So if we look at a little picture here, plasma is a gas that has had so much energy applied to it, so much heat or pressure or both, that the electrons have been stripped away from the nuclei. So it's just free-floating electrons and free-floating nuclei, protons and neutrons. And it can conduct electricity. Plasmas are created when a large amount of energy is applied, like I just said, to a gas, and the electrons are ripped away from their nuclei. Energy can come from high pressure, high temperature, or a strong electromagnetic field. Interesting. So here's some examples of plasma. The sun, the hydrogen gas, and then the small amount of helium gas, smaller amount of helium gas, and the sun is all in a plasma state because of the intense heat and pressure. The electrons have been ripped away from the hydrogen nuclei. And so that is the same as all stars are in a state of plasma. We can experience here on Earth lightning. Lightning is plasma. Everything in the early universe, right after the Big Bang, was plasma. Also fluorescent lights, those kind of tubes of lights, there's plasma in there. If you see a neon sign, that's plasma. And you're going to watch a little video and answer a few questions about that. And that's the end of the notes.